Hey there! Today, we're going to explore a really clever technique for finding that one single best answer, even when you're faced with what feels like billions of choices. So let's just dive right into the pretty elegant world of FIFO, branch, and bound. I mean, just think about it for a second. Imagine you're faced with a choice. But it's not just one choice. It's a whole cascade of them, where every single decision you make just opens up a dozen more. How in the world do you navigate a maze like that to find the one single perfect path? And look, this isn't just some abstract puzzle, right? This is at the very core of so many real-world challenges. Think about a trucking company that's trying to find the absolute shortest delivery route to save on gas. That's the famous traveling salesman problem. Or maybe an airline trying to schedule all their flight crews using the fewest people possible. These are called optimization problems, and trust me, they are everywhere. Now, you might have heard of a method called backtracking before. Branch and bound is kind of like its cousin, but it's different in two really key ways. First, it explores all the possibilities in a much more structured, orderly way. And second, it uses a much smarter way to eliminate the bad paths really early on in the game. To really get our heads around how this all works, let's use a metaphor. Let's just imagine we're trying to navigate this massive, incredibly complex map of every possible solution. In the world of computer science, we call this thing a state space tree. So, the very first step in navigating this map is to figure out how it's even drawn in the first place. And that brings us to our first big idea, the branching process itself. Okay, so here's the basic principle. Branch and bound works by picking one single spot on our map, we'll call it an E node for expansion node, and then exploring all of the immediate paths that lead away from it. We generate all of its children before we even think about moving to a new spot. It's a super systematic way of building out our map. And to keep track of where we are, we just need a few simple terms. A live node is like a place on our map that we know exists, but we haven't actually explored yet. The E node is the specific spot we are checking out right now. And a dead node, well, that's a dead end. It's a path we've decided is not worth our time. And that's really it. That's our first idea. We just branch out, systematically creating this map of every potential solution. Okay, so we're drawing our map. But with so many places to explore, which one do we go to next? This brings us right to our second idea. We use a rule called FIFO, and it's beautifully simple. It just stands for first in, first out. It means we explore the spots on our map in the exact same order that we discovered them. It's literally like waiting in line, or a queue. The first location we added to our places to visit list is the first one we're going to check out. You might also know this as a breadth-first search. And here's exactly how that queue works. So you find a new path, a new live node, you just add it to the very end of the line. Then, when it's time to pick a new place to explore, you simply take the node that's been waiting the longest, right from the front of the line. This makes sure that we explore the map, level by level, in a really systematic and fair way. It's methodical, it's orderly, it's just a simple, fair system for exploring a massive space. But here's the thing, being fair isn't always the fastest way to do things. Exploring the entire map could take forever. And this leads us to our third, and honestly, our most powerful idea, knowing when to stop drawing. So here's the crucial point. We really don't want to waste time exploring paths that are obviously leading nowhere interesting. I mean, if a path already looks like it's going to be worse than a pretty good solution we've already found, why bother with it? We need a smart way to prune these unpromising branches right off of our map. And we do this with something called a bounding function. It's a really clever two-part process. First, we're always keeping track of the value of the best complete solution we've found so far. You can think of this as our current high score. Second, for any partial path we're thinking about exploring, we calculate a super optimistic guess of its best possible outcome. And if that best case scenario is still worse than our current high score, well, we know it's a dead end. We just prune it and never look back. And that right there, that's the true power of this whole thing. It's not just about exploring, it's about the art of knowing when to stop. Okay, so let's put all three of our ideas together. We're going to branch out to make the map, we're going to use a fair FIFO queue to decide where to go next, and we're going to prune the paths that just aren't worth our time. Let's see how this all works together on a classic problem. We're looking at the 0-1 knapsack problem. So picture this, you're let's say, a collector with a knapsack that can only hold a certain amount. You've got a bunch of items in front of you, and each one has a weight and a value. Your goal is to maximize the total value of the items in your bag without going over the weight limit. This tree that you see here, that represents every single possible combination of items. This is our map. Right at the very beginning, of course, we haven't found any solution yet, so our high score, our best profit so far, is basically nothing. We're just hoping to find any combination of items that can beat, well, 0. So here we go. We start at the top, at the root, node 1. Following our FIFO rule, we generate its children, that's nodes 2 and 3, and we add them to our queue. Then, we take node 2 from the front of the line and we expand it, which creates nodes 4 and 5. Then, we expand node 3, which creates 6 and 7. You can see we're just systematically exploring our map, one level at a time. Now, as we keep exploring, we eventually reach a node that represents a full, valid solution. Let's say it's node 10. We calculate its profit, and it's 38. Fantastic, we have a new champion. Our current best is now 38. And this is huge, because any path that can't possibly beat a profit of 38 is now on the chopping block. And this is the magic moment. Let's look at node 7. We calculate its optimistic estimate, its best-case scenario profit, and it turns out to be 28. Well, since 28 is less than our current best solution of 38, we know with absolute certainty that no path starting from node 7 is ever going to beat our current champion. So we just make it a dead node. We prune this entire branch of the map without ever having to explore it. What a time saver. And you just repeat this process. You expand the next node in the queue, you update your best solution whenever you find a better one, and you prune any path that just can't measure up. And by doing this, we eventually explore all the promising avenues, and we find the optimal solution, that maximum profit of 38, and we did it without having to search every single node in the tree. You know, the FIFO approach is fair, it's systematic, and it guarantees we find the best path. But it does kind of explore blindly, just going level by level. So what if? What if we could use our bounding function, not just to prune paths, but to actually guide our search toward the most promising-looking nodes first? You know, when might it be better to be a little less fair and a whole lot more strategic?